Now we have the talk by Abner Sampaio. He is a doctor at UNIFESP.
Thank you, Jonathan. Good morning, everyone. I'll talk to you about our work comparing the performance of sulfonium and phosphonium-based ionic liquids as electrolytes for supercapacitors biomolecular dynamics simulations. So supercapacitors are devices that can store energy by the adsorption of ions on the surface of electrodes without any chemical reactions. Here we have a Hagone plot. This is a graphic used to evaluate the performance of a lot of electrical devices. And we can see that electrochemical capacitors or supercapacitors usually present a lower energy density and a higher power density than the common batteries such as lithium-ion batteries. So the challenge here is to enhance the energy storage of supercapacitors without losing power performance. As we can see, both energy and power are proportional to the square of the voltage. So one way to face this challenge is to use electrolytes that can support work at higher operation voltage conditions. And that's why ionic liquids are considered good electrolytes for supercapacitors. Ionic liquids are molten salt at low temperatures, usually below 100 degrees, and they present a lot of interesting properties. And despite the fact that they present a higher viscosity and a higher cost than usual electrolytes such as aqueous electrolytes or organic-based electrolytes, the main advantage of the ionic liquids is their high electrochemical stability and their high thermal stability. So in our work, we simulated two different ionic liquids, sulfonium-based ionic liquid that is formed by this cation and this imidine ion. And the second one is a phosphonium-based ionic liquid formed by this phosphonium cation and this imidine ion. Both ionic liquids present a low viscosity compared to other common ionic liquids, similar ionic conductivities, and wide electrochemical stability windows. So we put the ionic liquids between two slit nanoporous electrodes. These are graphene electrodes, and the pore size was 12 angstroms. We simulate them on lamps with constant potential, which means that the charges on the electrodes are able to fluctuate over the entire simulation time in response to the interactions with the electrolytes. So first of all, we have here the accumulated charge on the negative electrode for both supercapacitors. We can see that in the supercapacitor with the sulfonium ionic liquid, the accumulated charge is always larger than the accumulated charge on the phosphonium-based supercapacitors. And this happens because we have a larger difference between the number of counter ions inside the electrode in this supercapacitor than in the supercapacitor with the phosphonium electrolyte. So this happens because the sulfonium cation has a smaller volume than the phosphonium cation. So it allows to have a larger number of counter ions inside the negative electrode pores. This is important because when we calculate the energy stored by these supercapacitors, we can see that the supercapacitor with the sulfonium ionic liquid can store more energy than this supercapacitor with the phosphonium ionic liquid, despite the fact that phosphonium ionic liquid presents a higher electrochemical stability. So this is in a first moment unexpected, but considering the limits of the electrochemical stability window of the sulfonium ionic liquid at 3.8 volts, the supercapacitor with this ionic liquid can store almost 50% more energy than the supercapacitor with the phosphonium-based ionic liquid. So we can conclude until here that the better performance of the sulfonium ionic liquid is due to the small size of the sulfonium cation in comparison with the phosphonium cation, which allows for a large number of counter ions inside the negative electrode pores. But the energy stored by the supercapacitors aren't the only thing that is important about the performance of the supercapacitors. Another important thing about these supercapacitors is their charging dynamics. And we use that transmission line model to evaluate the charging dynamics of these supercapacitors. This is a model that is used to analyze experimental results of impedance spectroscopy. In the general form of this model, we have infinity RC equivalent circuits connected, And the main consideration of this model is that the electrode charges progressively from the electrolyte interface to the bottom, showed by these arrows. In our systems, we consider that the electrodes are formed by two slices of RC equivalent circuits, and we have a capacitance, different capacitance for each slice, but the resistance for each slice is the same. So for a RC circuit of this model, we can solve the equations, the differential equations that describe them, and the result will be these equations, this equation that we can fit to the charge data that we get from our simulations. Actually, we do not fit these equations directly. We need to solve these other equations and write these four parameters as functions of the resistance in the bulk electrolyte, the resistance inside the electrode pores, and the capacitance of each slice of our RC systems. At the end, the only unknown parameter here is the resistance inside the electrode pores. So first of all, we have here this graph that show that the function is well fitted to the charge over the entire simulation time. And we can see here that the resistance inside the electrode is twice as larger for this phosphonium-based supercapacitor than for the sulfonium-based supercapacitor in the two charging simulations we performed, from 0 to 2.55 volts and from 0 to 4 volts. This result here is important because it suggests to us that the mechanism of the charging mechanism of these two supercapacitors are different. The charging mechanism of a supercapacitor can be a counter-ion adsorption mechanism in which the main process here is the adsorption of the ions on the surface of the electrodes. It also can be an ion exchange mechanism in which the main process is the swap between the ions inside the electrodes and the ions outside the electrodes. And it also can be a co-ion desorption in which the main process is the desorption of the co-ions from the surface of the electrode. And we can quantify this mechanism by this X parameter. So we analyze the X parameter over this entire simulation time. And we can see that at longer times, the ion exchange mechanism dominates the charge of both supercapacitors since the X parameter fluctuates around 0. But in the positive electrode, the difference between the behavior of the X parameter is too small. But the negative electrode, we have important contribution of the counter-ion adsorptions. Since in the sulfonium-based ionic liquid, we have the X parameter starting at 0.5, and in the phosphonium-based ionic liquid, it's almost 0 in the start of the simulation. So it is also determining the fast charging dynamics of this supercapacitor with the sulfonium-based ionic liquid. And it is also an effect of the small volume of the cation in comparison with the anion and the phosphonium cation. We have here actually when the anion leaves the pore of the electrode, we have a higher or a larger free volume to the sulfonium cation than for the phosphonium cation, and that's why we have more cations inside the electrode in the supercapacitor with the sulfonium electrolyte than the supercapacitor with the phosphonium electrolyte. From this resistance inside the electrode, we can calculate this tau macro. This is a parameter that means the time in which a real supercapacitor will charge. And as we expected from the resistance inside the electrode, the tau macro for the sulfonium-based supercapacitor is smaller than for the phosphonium-based supercapacitor, which means that this supercapacitor charges faster than the supercapacitor of the phosphonium cation. And we compare it with a result for supercapacitors with MOF electrodes. This is a paper published here recently, and we can see that the tau macro is comparable to real supercapacitors. This is actually an experimental study, and we can see that And we estimate a Hagone plot for our supercapacitors. And we can see that besides the fact that the tau macro is compared to the real supercapacitor, we have also similar performances. So what we simulate here is not so far from the reality of we have about supercapacitors today. So to conclude, in spite of the narrower electrochemical window of the sulfonium supercapacitor, the sulfonium ionic liquid, the similar viscosity and the ionic conductivity of these supercapacitor, these ionic liquids, the sulfonium-based ionic liquids provides a large stored energy in these slit porous supercapacitors of 12 angstroms. It also provides a faster charge dynamics, which is related to its higher power. Then we think that the sulfonium-based ionic liquids is a promising electrolytes for supercapacitors. And we think also that the experimentalists should try to study this kind of devices and evaluate if it's okay with the reality. And we also showed here that applying molecular simulations in the transmission line model, we can perform the multiscale simulations since we can extract some multiscale, macro scale parameters. So if you have a way to go, we think that the supercapacitor with sulfonium-based ionic liquid should be here in this Hagone plot. This represent great enhancement of the performance of a supercapacitor compared with we have in this graph. So I would like to thank you, thank FAPESP, thank CINE-CMSC and our laboratory at UNIFESP.
Okay, now we open for questions, the audience.
I'm sorry, I'm quite late on that. But what's the Hagone plot? Would you please explain again because I couldn't understand?
This is a graphic that makes a relationship between the specific energy of electrical devices and the specific power of the an electrical device. So we can see how much energy electrical device can store, and we can see also how many power it can uh, uh, how many power it is he can present. So we can see how much energy the device delivery and how much energy it's stored, and it also have here the time in which the process of delivering and charging of these supercapacitors or batteries can happen. I don't know if I was clear.
On the beginning of your talk, you show a figure that you concern the geometry of your supercapacitor. Okay, does your results depends how you build up this initial geometry, especially on the left and the right sides? Then, for example, if it depends, how you are sure that you are in the right approach to describe the physical system?
Now understand the don't depends. The charge on each electrode, the charge accumulate on the negative and the positive electrode is the same. We we consider that when we calculate this energy.
Can you explain how do you define the volume in your systems when you compare the both capacitors? Because I don't understand how do you compare when one capacitor have a small volume than the other.
We put the same number of ionic pairs to simulate the two supercapacitors. In practice, the volume is different, but when we calculate all these properties such as the energy or we estimate the power of these supercapacitors, we do that by the mass of the electrodes, and then we use that to compare the properties of these two. Just actually use only the number of ions of the two supercapacitors. It depends actually on the bulk density of the ionic liquids. We need to guarantee that in the bulk, the density here is the same if we would simulate the bulk ionic liquid. It can't be lower or higher than the bulk density.
Okay, we have more questions.
When we use the transmission line model, we need to be very careful with the way we will divide this electrode, and we use it only two because of the small the electrode is too small to divide it in more slices.
We have more questions. Seems that's not the case. Let's thank the speaker again.